Hi, welcome back to Noel Zura Labs and welcome to 2026. In today's video, we're going to take a look at Anycast. I was having a conversation the other day with a friend and they asked me, aren't IP addresses meant to be unique? And I said, yes, but they have to be unique on the network. So now what you need to understand is that when we have the internet is made up of multiple networks. Different ASs make up all of those different networks, and then they share routes to each other. So for Anycast to work, it's reliant on using routing to route the client to the closest network that is offering that IP address. So take, for example, if we had a DNS service like Google's 8.8.8.8, everyone in the world all over is not just accessing 8.8.8.8 in a server sitting in Google's campus. Well, they have got multiple servers hosted by different ISPs, different carriers, different content providers, and they have those servers sitting in those locations. But if they all had different IP addresses, everybody would have to remember what the IP address was, which one is their closest. Everyone would have to go and look it up. It would be pretty painful. So to get around this, we can use the same IP address and we can steer clients by using routing towards a network that is offering that IP address and allow them to access the closest one. In the event that there's a failure, the client will access the next one. So in the lab, I've got a brief demonstration of how this works. So let's jump in the lab and give you an overview. Welcome to the lab. Now, whilst these nodes boot up, let's have a brief discussion of what we're looking at here. So what we've got is 4 different autonomous systems. So these could be 4 different carriers. This could be a client of another carrier that is connected to that carrier, and then another carrier peering with another carrier. They're just different autonomous systems connected and peered. So what we currently have set up is we have AS101 is currently has a peering with AS102. Now they have clients being advertised out of their 10.1.3.0/24 network and 10.1.4.0/24 network. So this AS is advertising its /24. This AS is advertising its /24. That is how the two clients are able to reach each other, and the two autonomous systems are receiving each other's advertised networks. These are what we are simulating here is like an edge of an autonomous system. So this would be like the edge of an autonomous system using an external BGP peering to another autonomous system. So at the moment, I've got this set up so that the two clients can reach each other, and we'll test that in a minute. And then what we're going to set up is these two ASs up here, AS104 and AS103. Now they're going to have a peering with each other, and they're also going to peer to AS101 and AS102. This way, what we should see is that when this client would like to access this Anycast IP address that we're going to have, which is going to be 10.99.99.99, this client should go to node 1. Now the reason it would go to node 1 is because it's the shortest path. If we look here, it's going to come into its AS, it's going to leave its AS, jump one hop over to AS104 and into the node. If we wanted to reach the Anycast node being served by AS103, which is also advertising the same IP address, it would have to take multiple hops to get there. So it's further away. So the routing decision that this router here would make, unless we manipulate it by changing its the path or the weight of which one we would like to use in which direction, it will take the shortest path. So it will go, hey, the route for this network, the quickest way to get there is via AS104, and it's going to go to AS104. Likewise, the client in client 2, when it has a peering with 103, it's going to say, hey, my quickest route to 10.99.99.99 is via AS103. So it's going to go there rather than going across either to AS101 up to AS104 and across, or 103 and over to 104 and across, because all of these will have a peering. So by default, BGP will pick the closest, the same as like how we have OSPF, open shortest path. It wants to pick the quickest way to get somewhere. It may not always be the best way, so that's why we have methods of manipulating the routing metrics that these protocols use, so that we can make decisions as human beings about, actually, I want AS102 to use this node over here because this is, say, a 100 gig link, and this is a 100 gig link, and this is a 10, and this is a 10. So we can manipulate the path using those methods. So now if we look here for node 1, it should have fired up by now. We'll have a look at the networking configuration of this Linux box. It is just a Linux box. And if we take a quick look at the net plan, so sudo nano /etc/net plan. Now we can see that the server does have a unique IP address on its physical interface. So it has a physical interface, which has a unique IP address for its network. We can see here 10.1.1.0/24. It's got an IP address of 10.1.1/.2/24. And it's going to the default gateway, which is this router here, of 10.1.1.1. We can also see that it's got a loopback interface. So this IP address and this interface is to the node. It's not on the physical network, it's behind this IP address. So 10.99.99.99/32, single IP, is assigned to L0. And we can see that the only way to reach that is via this node. So you can see where we're going to go here. If we take a look at node 2, and we do the same, do it a different way. Permission denied, okay. We can see again, we have a loopback address of 10.99.99.99. This could be 1.1.1.1 or 8.8.8.8. So this is our Anycast IP address. And we can also see that we have a physical address of 10.1.2. Find the machine. 10.1.2.2 and the default gateway 10.1.2.1. So again, to reach this Anycast address, we have to route through here. So in simple terms, we're going to put a default route. We're going to put a route on here saying that any traffic that would like to reach this Anycast address is going to be behind this gateway. So, and each node is running a web server so that we can test to each of them from the clients. And what we're going to do is we're going to configure BGP peering. We're going to advertise our Anycast address from AS104 and AS103. And then we're going to test from client 1 and client 2 and see which node that they actually travel to. And then we're going to perform like a failover and a couple of different failover methods to remove that route from being advertised, to then see the client fail over from one node to another. And then that way we can maintain not only high availability for our clients, we can guarantee that when the node comes back up, our client will go to the nearest node. And then that can help reduce latency, especially for services online that need low latency. This is very helpful for that. So client 1, when we advertise this, it will reach this node here. And then in the event of a failover, we expect the advertisement for node 2 to be inserted into the routing table of AS101, and it will make its route and make a path to AS103 to reach that Anycast address. So let's just jump now onto our two clients and our AS101 and AS102, and we'll just have a brief look at the configuration there, and we'll check that the two clients can reach each other. We will then set up AS104 and AS103. We'll do a peering between the two of them, and then we will peer to our downstream client networks, and we will then test access to our Anycast addresses. So let's do that now. Okay, so here's AS101 and AS102. So if we do a show run, we can take a look that we have already configured our basics. Obviously, if this was a real Edge AS router, it would have a loopback address. It would have OSPF configuration for its underlying OSPF configuration. It would have next hop self for its to advertise any of the routes it received to its internal BGP peers, but we're obviously not doing that here because we're just using the Edge routers, and we are just concentrating on how BGP selects its path to an Anycast IP address. So we can see here that our BGP router configuration for AS101, we have a peering to AS102. We've already pre-configured the peering to AS104, but it's not currently up. We are advertising our client network into BGP, and we have activated the connection to our nodes. There is no other routing in place. There is no other IP route. So if we do a show IP route, there's no static routes configured on here. We just have our directly connected networks, and we have our BGP network that is being advertised to us from AS102. So AS102 is advertising this 10.1.4.0/24 network to us. So if we look again over on AS2, we can see again, we have a brief skeleton template of our IP addresses for our interfaces, but the main concentration here is our BGP configuration. We have a peering with AS101. We are going to have a peering with 103. I've already pre-configured this side again, but only the network peering to 101 is currently up. We are advertising our network, and we can see that there is no other static routes. So show IP route. We have no static routes involved on our client networks. We are just receiving routes via BGP. If we do a show IP BGP, we can see that there we go. We are receiving the 10.1.3/24 from AS101. And we can see that we're advertising 10.1.4.0. So that's our two client networks. They are up and running. Let's just double check from our clients that they can ping each other. 10.1.4.10, sorry, is the address on the client. Try ping 10.1.4.10. There we go. Okay, so we have routing working between our two clients. So our two client networks are connected to autonomous systems, advertising their networks, they can reach the clients. Let's create a peering from AS104 to AS101, and let's advertise our networks to the rest of the world. So let's connect to AS104. Check that all of our physical interfaces are up and we have an IP address. That is all we need right now. So that is good. Let me move this over here so we can see what we're looking at. So our IP address for G0/1 is 2.6. This is 2.5 over here. So we're going to create a peering to 2.5. So config T, router, BGP, our AS number is 104. Our BGP default, sorry, our BGP router ID is going to be 4.4.4.4. Not that it really matters here. We're going to create a neighbor to 172.21.2.5. We know that the remote AS is going to be 101. And then going to jump down into our address family, IPv4, and we are going to advertise a network. We're going to advertise, not only are we going to advertise the /24, we're going to advertise our Anycast address, because there may be an instance for management reasons. We may want to manage this node using its directly connected interface whilst from anywhere in the world. So obviously that we want reachability to that. So network, we're going to advertise our 10.99.99.99. Mask is obviously 255.255.255.255. And we're going to advertise the network 10.1.1.0. Mask is 255.255.255.0/24. Neighbor is 172.21.2.5. We're going to activate that. I think it's already activated anyway. And soft reconfiguration inbound, so that we can keep the routes in memory for viewing them. So that should be it for that node. We will jump back up and we'll do our neighbor relationship over to AS103. So neighbor is going to be 172.21.1.2. The remote AS is going to be 103. And again, address family, IPv4. We're just going to activate that. So that will be 172.21.1.2. 25, 1.2, and we will soft reconfiguration inbound on that. So what have we got so far? Let's have a look. So if we do a show run, we can see that we have made our configuration. We've got appearing to AS103. We're going to create appearing to AS101. We've done our basics. We've advertised our two networks that we want to advertise. We've advertised our network, and we've advertised our Anycast address for our server that we want to access. Now, if we jump back over to AS101, we can see that we have a neighbor relationship up. If we do a show IP route, we can see that we have two BGP routes in there now. We now have the route to the 10.1.1.0/24 network. That's fine. And if we jump onto the client, we can see that the client can ping 10.1.1. What was it? 2. So there we go. We can see that we can reach the actual node. We can see that we can, if we open a web browser, we go to 10.1.1.2. We can see we can reach the box, but we're not using the Anycast address, which is not what we want. We don't want our client to have to remember that to access this node, you have to use 10.1.1.2, and to access this one, it's 10.1.2.2. So we're going to use the Anycast address, but we can see it's not being advertised. So if we jump back over to AS101 and we do a show IP BGP, we can see that we are not being sent from AS104 the Anycast address. So the reason that is because the Anycast address is not in the routing table of AS104. So it's not going to be able to advertise it because it's not a directly connected network. So we're going to put in place a pull-up for this. So IP route 10.99.99.99, 255.255.255.255/32. And the next hop for that address is going to be 10.1.1.2. So now if we come over to AS101, we should see that Anycast address in our table. So we have now received the Anycast address. So client 1 should now be able to ping 99.99.99, which it can. It should now be able to go to 10.99.99.99, and it can. It's reaching the node 1, which is what we want. That's good. So if we take a look now at node 2, so first of all, let's jump over to node AS102. Let's have a look at the BGP table in here. You can see currently it's receiving the path for the server that we've configured, our Anycast server, it's going via 101 to then 104, because at the moment this AS only has a peering here and this node has a peering here, so it's advertising the routes over to this AS. This AS is able to reach that network via AS 101. It's not going up here because we don't have that peering live yet, and we don't have a peering from here to here yet. So, or we don't have a peering from here to here, sorry. So what we'll do now is we will configure our, let's test from client 2, just to prove that it can reach that address as well. Need to clear these down. I've got too many of these open. Let's close that one, keep that one, close that one, close that one. I only need to click on it once, so we want client 2. Test 1, 2, 3. So we are connected. So now let's open our browser and go to that Anycast address. And we should see that we're going to go to the node that is currently up and reachable, which is node 1. So if we go 10.99.99.99, there we go. We are reaching the Anycast IP address of node 1. Good. So both of our clients are currently reaching our first node. So that's all good. That's how we expect things to be working. So let's jump back over now to node 3 or AS 103. See what we've got configured here, pre-configured. No BGP. So now let's create our BGP peering from AS 103 over to AS 104 and down to AS 102. And again, we will then do a pull-up route and we will advertise the Anycast address as well. And what we should see happen is that our downstream node should have a route in the BGP, received BGP table to both of these networks via different routes. But we'll see that this side will say, hey, this is the closest one, and it will use this one. And once we start advertising over here, we'll see that client 2 will actually take the path to node 2 because, again, it's also the shortest path. So let's do the same over here. Let's start with our router, BGP 103. Our BGP router ID, not that it really matters, is 3.3.3. We're going to have a neighbor relationship. Let's pop that there. We are going to have a neighbor relationship with 172.21.1.1, and the remote AS is going to be 104. We're also going to have a neighbor relationship to 1. This is G0/1/5, so that's 6. So we're also going to have a neighbor relationship to 1.6, and the remote AS on that side is 102. And we'll go down to our address family. And we will advertise network. We will advertise the Anycast 10.99.99.99. The mask 255.255.255.255. We will also advertise the 10.1.2.0. So network 10.1.2.0 mask /24. And again, we will activate to 6. We will activate over to 1. And we will do our soft reconfiguration inbound so that we can see the routes. Now we know we need a pull-up route as well. So we're going to IP route 10.99.99.99. And we know that a static route has a lower metric. So it's like lower than BGP, which is like 20. So this will take precedence over the route it receives from AS104. Because if before I put this route in, let's just show that quickly. So if I do show IP BGP, we will see that AS103 is receiving a route to 10.99.99.99 from this path via AS102 to 101 to 104. And we can also see that it's got a path to it via 104. So you can see this little symbol here. That's showing you that that is the installed route into our table at the moment. And so, and why is that the installed route? It's the installed route because it's got the shortest path. So to get to this node via this path, we've got to jump through two other autonomous systems to get to AS104 and to reach that Anycast address. Whereas at the moment, it's going, hey, I've got a direct peering to AS104, I'm going to use that. And if we do a do show IP route, we will see in our table a route to 10.99.99.99, but it has a metric of 20, and we're going to put a static route in, which has a much lower metric, and so it will take precedence over that, and we will remove this from our table, and we will take this route. Later, when we do some failover testing, we'll show two ways of how we can manipulate so that the route comes and goes out of the table automatically, depending on where the link goes down. But for now, let's add our IP route 10.99.99.99, 255.255.255.255, and we're going to send that to 10.1. What did I say? 2.2. So now we're saying, hey, on here, we're saying manually, if you want to reach this Anycast address, it's via node 2. Don't worry about anything that you receive. So now again, if we do, we will see that we are still receiving it via BGP, but we can see the two routes that are valid are the one that we're advertising outbound and the one that we're receiving from 104. So now if we do a do show IP route, we will see that our route to there is now a static route and not the one via BGP. Good. So that should be enough for us to get started on this. Let's just save this. So if we do a show IP route on AS104, we can see that it has its static route to the Anycast address, and it will then use that and advertise that out. If we have a look at AS102, we should now see that we have received a route. We can see that we have now received a route from AS103 for the 10.99.99.99 Anycast address, and it's saying to send it over to AS103, and it's directly, it's like one hop. The path to it is straight away. So we can see it's got the little triangle next to it. That shows that it is the installed route into the, or is going to be the one that is installed into the table, into our routing table. So if we do a show IP route, we can now see that we're going to go via 172.21.1.5. 172.21.1.5. So now if we jump onto client 2 again, client 1, client 2. Now if we refresh this page, there we go. We can see that we are now reaching node 2. So we can see that our two clients, if we bring up client 1 and we refresh, we can see that client 1 is taking this path to the IP address. Client 2 is taking this path to the IP address. So the reason there's no IP address issues is because this is routed, it's not switched. The Anycast IP address is behind another IP address, so technically it's on a network. So on this network, that IP address is unique. So we can't have the same IP address on this segment. If we had a switch coming off and we put every IP address the same, it wouldn't work. There'd be an IP clash. But we could have multiple nodes behind here with a gateway, again, with an Anycast address. And then we could then, depending on which node is up on the router, we could say, hey, we could put an SLA monitor in place, and we could say, hey, if this node's not up, take that static route out and go to node 3 in this data center. And then BGP will still advertise that it's advertising 10.99999, and all the clients will still go there and go to the third node that we may add. But at the moment, we're just testing how you'd reach it globally. So we could say that this is one side of the world, this is the other side of the world. So at the moment, if client 1 is sending traffic to 10.99, it's going direct. Let's move that over here. So this is client 1. It's now taking this path up here. So what happens if we jump onto AS104, and for test purposes, we shut down this interface to simulate this server getting disconnected. Obviously, in the real world, there may be switches here, and we'll show that we may have to use like an SLA monitor so that we can monitor the node locally and remove it from the table. So if we take a look onto AS104, and what we will do is we will shut down int g0/2. So config t int g0/2. I'm going to shut that. So we can see that is now shut. We can see we're still pinging. If we go up here and we refresh, we can see that client 1 is now accessing the Anycast address via the node that is on the other side of the world, node 2. So we can see that that's the redundancy. Now let's bring that interface back up. So we'll bring that back up. We'll keep looking at node 1. We can see it's still pinging, happily pinging away. Let's do a refresh. We can see that client 1 is now accessing the Anycast address over here being advertised by AS104. Perfect. So you're like, hey, that's a good system there. That's working. Let's just double check with node 2. So if we bring node 2, client 1, node 2, let's put node 2 over here so we can see. Let's move you out of the way. So we've got client 2 going to node 2. So now if we send some ping traffic from node 2, ping 10.99, we can see client 2 is pinging the Anycast server address. If we click refresh, we can see by the web server that's running on there, it is going to node 2. Perfect. Let's jump on to AS103 and let's do the same test. Int g0/2. Let's shut that interface. And what happens when we shut that interface? If we do a do show IP route, because that directly connected network for the static route we put in place is no longer present, it gets removed from the routing table. So when it gets removed from the routing table, what happens? The route that we're being sent via BGP takes its place, which then means that the clients downstream, there we go, now going to node 1. We can see that we haven't missed a beat here. 55 sent, 55 received, 0 loss. We can see the client didn't even know that it's gone to a different node. It may see that there's an increase in latency depending on where these servers are in the world, that now client 2 is accessing this one. We may see that, or it will see an increase in latency. So that's why you can tell that there's a failover by looking at the latency. Let's bring it back up and let's show what would happen if, say, the server would go down. And this is where we're going to now make a change. So if we no shut that, so that brings AS103 interface back online towards node 2. If we have a look, we can see the interface is up. So again, if I do a do show IP route, we can see now that the static route comes back into play. Why? Because the directly connected network, the hop, is up. So that route is valid. Our router puts that back in the table over the BGP one because it has a lower metric of 1 instead of 20. And then we then advertise that out to our clients. And now again, if we jump back over to node 2 and I hit the refresh, we can see that it's now accessing node 2. So perfect. So at the moment, everything's working as we expected. Client 2 on this side of the globe is accessing the nearest node when it's online. When it fails over, or then this interface drops, it goes over to node 1 on the other side of the globe on a different network for failover. And the same thing here, client 1, this is its closest node. It's the shortest path to it. It goes to it, reaches it perfectly fine. Now, what would happen if I was to just shut down node 2? So if we shut down node 2 and I come over to here, I hit refresh and I send a ping, you can see nothing's working. Didn't change over. Why? This could also be, again, because this is an even G thing and it doesn't manually drop the actual interface on G02 when I shut this node down. But this can also happen in the real world. Say if this node was not directly connected to G0/2, G0/2 was connected to a switch and there was a data center or a rack and we had multiples of these servers in the rack. Each one of these servers is connected to the switch. The interface on the switch would go down, not the interface here. So the route wouldn't move because technically it still thinks that it can reach the network that's configured on G0/2 because the IP address that's configured there will still be showing as connected. So what we're going to do is we're going to put an IP SLA in place and monitor if this node is up or down directly and use that to remove or add the route back into the table depending on if this node is up or down, or if this interface is up or down. So let's start this back up. And we should see it reach again. And then there we go. It's pinging it now. It's now reaching that. So what we will do is we'll jump onto AS103 and we're going to manipulate the configuration a bit more. And we're going to put a IP SLA in place so that we can monitor the actual node, not the Anycast address. We're going to monitor the physical interface of node 2. So IP SLA 1. I'm going to do an ICMP echo and I'm going to ping to, what was the IP address again? It was 10.1.2.2. The source interface for that is G0/2. Should be it. And the IP SLA schedule 1, lifetime forever. I'm going to start that now. Perfect. And then I'm going to do a track. I'm going to track 1 IP SLA and I'm going to track SLA 1 and I'm going to check reachability. So that should be enough for that. So let's do a do show track. Reachability is up. So show IP SLA summary. We can see that that is working. Our router is testing connectivity to this interface. It's reachable. So now let's do a do show run. Now let's change our route so that it's controlled by that SLA. So what I'm going to do is I'm going to remove this route. and then I'm going to add it back in, but I am going to track 1, which is what I configured as the object. So now, show IP route. Good, we can see the route is in place. Show IP SLA summary. We can see that the node is up and working. Let's check. Let's bring up node 2. Let's move you out of the way. We can see that node 2 is going, client 2 is going to node 2, which is what we expect. It's pinging. Now let's stop node 2. Do a refresh. Now there'll be a slight delay now whilst the monitor detects that the node has gone down. So we'll see this happen on AS102. We'll see a console message tell us that it's gone. Probably take about a minute. There we go. We can see reachability is down. We can see now that the client is now going to the secondary node. Let's stop that ping. There was a little bit of loss whilst that happened, but it's back up. The client is now working again. The length of time that took for the changeover is kind of acceptable for things like DNS. You've seen it happen sometimes when you're sitting at home. You'll get that brief blip from your DNS provider, and plus you would normally have 2 DNS nodes anyway. So we'd probably have a primary and a secondary node on DNS that would be running in both of those locations. So before we even got to this stage, the secondary DNS server would have been handling the requests. So now if I bring that back online, what we will see now is that client 2 will revert back to accessing node 2. We will see the track change to up. So at the moment we've got a timeout. We'll see that change to up. It will reinsert the route back into the table. BGP from AS103 will start advertising that Anycast address again. We can see a reachability is now changed to up. If we check our IP route, and there we go, we can see that there was a slight blip and change there. Whilst that happened, we can see that the static route is back in place. So we can now see that client 2, whenever this node gets switched off, or if this interface goes off, the route gets removed, client 2 accesses node 1 or node 2. Everything's all perfect and right in the world. We can probably lower that timeout value again on the SLA monitor to give us an even quicker route removal and changeover. That's a demo of how Anycast works. There's obviously different ways that we can do this. We could have the node running things like free routing on Linux, and it could then advertise this 10.99999 Anycast address via BGP to the router here, and then the router will then re-advertise it. But again, just showing you with the static route gives us an overview of how it works and an understanding of what it's doing. So the idea of Anycast again is so that we are routing to an IP address to reach the best and the closest node that is up. Okay, and then for one final test, like I said, Anycast relies mainly on being able to route to a network. So obviously we can manipulate the route. So what if we said it was the other way around? What if we said for this AS, the best node is actually node 2 because it's actually closer. Just because it's laid out like this in the topology on the diagram doesn't mean that geographically AS101 is closer to node AS10 to node 1. It could be that AS102, yes, it's directly peered to AS104, but due to latency, node 1 is, say, in Japan. So there's a 300 millisecond latency from AS101 over to node 4, to node 1 in AS104. So we may want to say, hey, actually, our clients on this network actually want to be reaching node 2 most of the time, because node 2 offers us lower latency. It may be more path hops away, but it's it's a lower latency node for us, and it's closer geographically to us than node 1. So in AS101, we're going to manipulate this now and change the weight preference for the routes that we receive, because obviously if we jump into AS101, we can see that we receive the Anycast address from AS104. We also receive it from AS103 via AS102. So yes, it may be more hops away, but for us, actually, the node in AS103 is actually closer to us geographically. So let's make a change on AS102 and 101 to say, hey, I would actually prefer you to use this route over this one. So we do that by changing the weight. So let's jump into our BGP router, or router BGP, sorry. And we are AS101. Going to jump into our IPv4 address family, our IPv4 address family. And we are going to, for our neighbor, we're going to set our neighbor 172.21.2.2. So this one, we are going to give that a weight of 500. So this one here, we prefer this. And then what we'll do is we'll give the other one 172.21.2.6. We will give that one a weight of 400. So again, like with all of these metrics, sometimes it's the lowest one, sometimes it's the highest one. In this case, it's the highest one. The one with the highest weight is the path out of the AS that we're going to take. So what we're using the weights to do now is we're manipulating the path out of our AS that we want to take. We're going to say, hey, we want to reach this Anycast address, but we are giving a higher weight this way. So we want to send it this way because this one is more geographically closer to us than this one. So once we've done that, we're gonna clear our BGP session just to make sure that it changes over. So we will clear BGP IPv4 we'll clear all of our peers. There we go. So we're going to clear our neighbor relationships. Our neighbor relationships are going to rebuild. If we do a show IP BGP again now from AS101, we can see once everything is updated, we're giving weight to AS500. We're giving the weight to this, anything that we're being, and all the routes that we are receiving from these of a weight of 400 and 500. So to reach any of these networks over here, we're going to take this way around. Again, we could put a route map in place and say, hey, if we receive a route, or we could put a prefix in and say, hey, if we receive a route for the Anycast address, we're going to send it this way, but anything else for that node, you can send this way. So now let's jump on to node 1, test client 1. And let's see if we can just ping. Right, so we are pinging the node. Let's hit refresh. We can see that client 1 is using node 2. Because yes, it may be more path hops away, but geographically that is a closer, more latency, lower latency node for our clients here. So we prefer to use this one than this one, which was the shortest one, because by default, BGP is using the shortest path to the address. So we've manipulated that so we can do that. The same thing will still happen if we stop node 2 What we will see is we jump onto node 1. There we go, client 1, sorry, I keep calling it node 1. If we hit refresh on there and we send some pings, once the route is withdrawn, and there we go, we can now see that the route has been removed. We can see that our client 1 is now using the other node, but it's taking a different path still. It's still taking the same path. It's going via, it's going this way around rather than this way. So again, if the whole of AS103 dropped, we would then start taking this way over to the node. So again, we can manipulate the path and manipulate the path for different routes, etc. So let's test if I was to drop AS103 completely. So AS103 got pulled out of the network, it dropped. See, it takes a little while for routes to be withdrawn with BGP. It can take up to 3 minutes unless we manipulate the timers. But once that happens and the route drops and it gets withdrawn, you'll see that client 1 will access node 1 again via a different path. All right, there we go. That took some time. We can see now in AS101, the path to the Anycast address is now going directly via AS104. If we see AS102, which was where we were sending the traffic, it now finally expired. Its timer expired, showing that the node had gone down between it, the peering had gone down between it and AS103. So now client 1 will be now taking that path, and it is now pinging again towards AS104. Can speed up that failover by manipulating the BGP timers. Again, this will be very network specific because you don't want BGP to be flapping all the time and routes being withdrawn, etc. We want our BGP session routing sessions to be as stable as possible, and we don't want them flapping all the time, withdrawing routes and inserting routes into the network, because that has to propagate and spread across all BGP peers. So we've covered a few methods of manipulating the BGP protocol to change how our clients can reach the two different Anycast servers, and we've shown how the Anycast addresses can be advertised via different autonomous systems and how our clients can reach the closest one or the one that we prefer. And in the event of a failover, of a complete AS failure or a node failure, the clients will make their way to the secondary node that is online, or the next available node that is online, still using the same IP address. So I just had a couple of slides just at the end here to show about how we can use the same IP address in multiple different geographically dispersed locations and adjust the routing behavior on our own BGP session to steer our way to the nearest node or the location with the lowest latency or the transit costs, etc., to reach that node for our benefit. And then in the event that there is a failover or something happens, we can still reach that same Anycast address because it will be receiving it via a different network location or from a different AS, and we will then take our path to the next one. So as we've seen, it's normally done via BGP. We're using route selection. The shortest path is by default. We can use policies and metrics to adjust that. Like we saw, we can make changes to say, hey, actually, this node over here at node 2 was actually our lowest latency node. So we kind of want to use that one first, and we'll use node 1 as our secondary. But they were all using the exact same IP address. As far as our client was concerned, there was no change in the IP address. They were still able to access the same service. So just a quick brief of where you'd normally see this in the real world. The real world would be things like DNS. Like we've all used, like we said at the start of the video, Google DNS 8.8.8.8, 1.1.1.1 for Cloudflare. They're hosting multiple instances of these services around the globe, and then what they're doing, they are using the feature of Anycast to then route a user to the nearest node to use that service. And as we've seen, it offers the benefits of being able to offer the client access to the nearest point of service, which gives them things like lower latency, lower jitter, faster download speeds, depends on what you're using. If it's a download server, you can mitigate things like DDoS attacks. So if one node is being attacked and that IP address is being attacked, it's being routed to whichever is the nearest one within that network. If you can see that the source is coming from one area of an AS system, we can black hole the traffic coming from that prefix and block it. So then the rest of the nodes will still be handling traffic for other customers. So it's built for scalability, reliability, and performance. And as we've seen, you can see how we can easily have the reliability and resilience. You can see how we can scale. We don't have to keep telling a user to use this IP address or this different IP address. So it makes life easier for our users. So there we go. We've seen how Anycast works, and I hope that answers the question of how we're able to use the same IP address for a service and have it not cause any problems and allow our clients to reach and access the services that they need, and have the clients not have to think about anything in return. So thank you very much for watching. If you've liked and subscribed, thank you very much. I know we've now hit over 500 subscribers. That's great. If you can now just all keep watching the videos, get those view numbers up, get the hours up on the watch time. Remember to like and subscribe, and I'll see you on the next video.